The announcement by Gemini Observatory that 3I Atlas is not traveling alone but appears to be escorted immediately forces us to reconsider what we understand about interstellar visitors. What we thought was a solitary traveler now seems to have company. For an object that arrived from beyond our solar system, moving on a hyperbolic trajectory, the presence of a nearby companion or escort upends the simplistic notion of a lone wanderer and opens the door to far richer possibilities about how interstellar objects behave, how they get ejected from other star systems, and how they might interact with the environment of our solar system. Before we start, smash the like and subscribe buttons for more updates. To begin with, the object in question, 3I Atlas, was already remarkable. It is only the third confirmed interstellar object to pass through our solar system, and one of the fastest, exhibiting an extremely hyperbolic orbit that clearly shows it is not bound to the Sun. Its discovery captured imaginations, the tale of a visitor from another star system, briefly making its appearance in our cosmic doorstep. Now, the Gemini images suggest that what we are seeing is not just a solitary comet nucleus with its outgassing coma and tail, but a complex system with a companion, perhaps a fragment, perhaps a co-traveler, perhaps a captured satellite of sorts. That suggestion raises urgent questions. How did the escort come to be? What does its presence imply about the formation, structure, and history of 3I Atlas? And what might this mean for our broader understanding of interstellar object dynamics? Imagine the scene. 3I Atlas hurtles through space toward the Sun, carrying with it a fuzzy coma, a nascent tail of dust and gas, and behind or alongside, a smaller object keeping pace, an escort. Gemini's observations, previously focused on the growing tail and increasing activity of the comet, now show hints of a discrete point or points of light moving in tandem. While the primary comet's nucleus dominates the brightness, and the extended coma hides direct view of the solid body, imaging sequences show subtle motion, trailing or alongside the main object, which cannot easily be dismissed as a chance alignment of a background star. The possibility therefore emerges: 3I Atlas is accompanied. If that is the case, the implications ripple outward. One immediate thought is fragmentation. Could 3I Atlas have shed a piece of itself? Perhaps during an earlier close passage to its parent star, or via internal stresses or volatile-driven outbursts. And now that fragment is traveling behind, still moving on a similar orbit? That would mean our interstellar visitor had already begun to break apart before entering our solar system, pointing to a far more dynamic history than simple ejection and inert travel. Alternatively, the escort could be a smaller body gravitationally bound to whatever remains of the nucleus of 3I Atlas, suggesting a binary or even multiple component system. If that is the case, we may have underappreciated the possibility that interstellar objects may travel as more complex systems rather than lone bricks of ice and rock. The presence of an escort also leads to questions about the formation environments of such objects. If 3I Atlas carries a companion, it invites memories of the small bodies in our solar system that travel together, binary asteroids, pairs of objects ejected together, or fragments that linger nearby. Perhaps the ejection mechanism from its original star system was violent but preserved a fragment pair, or perhaps the companion formed close to the same parent body and was carried out together. That would suggest the parent system's dynamics allowed for the ejection of a multi-body group rather than only single fragments. Interstellar cometary bodies, then, might come in groups. The timing of Gemini's imaging is also significant. One of the striking features of 3I Atlas has been its growing tail and active outgassing well before perihelion, moving closer to the Sun and becoming more active than many had anticipated. The fact that observations already showed a more extended coma and tail means the escort might have been obscured earlier, hidden by the brightness of dust and gas. As the comet continues to approach the Sun, the environment around it becomes more dynamic. Dust streams, solar radiation pressure, solar wind interaction, all of which could affect the relative motion of any companion. That the escort remains coherent enough to be seen suggests that the companion is not simply a random loose clump, but something coherent and enduring. Observers will now watch carefully whether the companion remains at a fixed relative distance, whether it diverges, or whether additional fragments appear. Another key implication concerns the interaction with the solar system's environment. As 3I Atlas sweeps through, its path takes it past Mars, then closer to the Sun, then back outwards. If the escort is real, then the system of primary plus companion is subject to tidal forces from the Sun, solar radiation pressure gradients, and possibly gravitational perturbations from planets. The dynamics of how a multi-body interstellar system interacts with our solar system are unexplored territory. Could the companion be stripped away or altered? Could it diverge and become a separate minor body in our solar domain? Might it provide a window into how interstellar objects evolve once inside a different star system's gravitational field? The discovery also raises intriguing questions about observational strategies and the record of interstellar visitors. Until now, the two confirmed interstellar objects, 2I/Borisov and 1I Oumuamua, were treated as solitary. If interstellar comets in fact tend to carry companions or fragments, we may need to revisit archival data to see if faint trailing bodies went unnoticed. We may also need to refine our search strategies. When detecting an interstellar object, astronomers might now look not just for the main body, but for accompanying smaller bodies or fragments moving in step. The escort of 3I Atlas is telling us that interstellar objects might be more like families than loners. Furthermore, the fact that Gemini's observations captured this is a tribute to the quality and timing of current telescopic assets. The Gemini Observatory, with its large mirrors and advanced imaging instruments, has allowed astronomers to monitor subtle features in comets and other small bodies in ways that were impossible a decade ago. The emerging picture of 3I Atlas being escorted speaks to how far we have come in observational precision and how our ability to capture minute details of objects many millions of kilometers away is now enabling new discoveries. That also means we might be on the cusp of discovering highly unexpected phenomena that challenge our mental models of how comets and interstellar visitors behave. If the escort is indeed bound, what might its physical nature be? It could be a small fragment of the nucleus that split off long ago, perhaps driven by internal volatile pressure or rotational spin-up. Alternatively, it might be a chunk of material released recently, now following closely. If bound, the mass of the companion relative to the main nucleus may be small, yet its motion reveals binding forces that suggest the nucleus might be massive enough to hold on to small fragments even during interstellar ejection. That raises the question, what happened in the original system to eject both the main body and its companion? Perhaps a close stellar flyby or the destabilization by a giant planet sent the bodies out together. The dynamics of ejection may favor grouped objects rather than solitary ones. Alternatively, perhaps the escort is not bound but simply a fragment released earlier and now traveling on a slightly divergent path, still close enough to appear as an escort. In that scenario, the interstellar visitor is a swarm or train of fragments, and we happen to see one of them because it's physically close to the main body. That would make 3I Atlas less of a single nucleus and more of a composite object, a mini-fragment train. If so, that suggests that interstellar ejection events might produce many small fragments, and what we detect is just the brightest member. The presence of an escort invites us to look for more faint companions trailing or preceding. The implications for the composition and age of 3I Atlas are also compelling. Observations so far have revealed that 3I Atlas is unusually rich in carbon dioxide, has water ice and various volatiles and dust characteristics that make it distinct from many solar system comets. If the object carries a companion, then comparative studies between the two bodies may be possible. Differences in dust production, coma development, tail morphology might give clues to how the fragment separated, how its exposure to the sun's heat differs, and how surface volatile depletion might evolve differently in the companion. In effect, this could provide a natural control sample, with the companion acting as a sibling body to compare. The existence of an escort may also enhance our interest in potential missions. Much of the prior discussion about sending probes to interstellar visitors centers on singular bodies. If multiple bodies are traveling together, the chances might increase of encountering a fragment or capturing comparative data across the pair. Even if a direct mission is still unfeasible due to high delta-V requirements, as has been shown for 3I Atlas in particular, the sheer fact of a companion raises the scientific value of the target. Two bodies, same origin, different evolutionary paths. Though a mission may still be far off, the escort adds to the allure. It is worth pausing to reflect on why this matters so deeply. Interstellar objects like 3I Atlas are not just curiosities, they are messengers from other star systems. Each carries chemical, physical, dynamical information about environments and histories outside our own solar system. If one arrives with an escort, then the message becomes richer. We get not just one data point, but potentially a system, a set of bodies with shared origin, but different stories. That means the tapestry of extrasolar origin grows in complexity, and our models must grow with it. The idea that an interstellar object might be accompanied implies that the ejection processes of other systems may produce families of fragments, or that traveling in pairs is comparatively common. Further, it invites a reconsideration of how we interpret the data from 3I Atlas itself. For example, the dust tail and coma shape have been under scrutiny. Gemini recently captured images showing a growing tail that is more extended than before. If an escort is present, some of the features attributed solely to the main nucleus might need re-evaluation. Could part of the dust and gas emissions be influenced by a companion's activity? Could perturbations in the tail direction or brightness fluctuations be due to interactions between the two bodies? In short, the escort may force reinterpretation of observational data already collected. The dynamic path of 3I Atlas through the solar system begins to loom as even more significant. Its perihelion is about 1.36 astronomical units from the Sun, just inside Mars' orbit, and its trajectory is retrograde and slightly inclined. At that distance, solar heating is strong enough to activate volatiles and drive dramatic cometary behavior. If the system includes a companion, the solar rendezvous might place differential thermal stresses on the bodies. The smaller fragment, if smaller, might heat and outgas at different rates, possibly evolve into a separated object visually. Observing the companion's behavior across perihelion may reveal divergence and help us understand how these bodies endure solar approach after interstellar travel. Another piece of the puzzle involves gravitational interactions. While the companion and main body begin traveling together, once inside our solar system, they are subject to the Sun's gravity, solar radiation pressure, and possibly perturbations from planets. With a companion present, the relative motion between them might change. The smaller body could be stripped away, drift behind, or even swing ahead depending on the forces at play. If the companion falls behind sufficiently, we might witness the creation of a mini cluster of interstellar fragments distributing along a trajectory through the solar system, or even one getting captured into a different orbit, though capture remains unlikely given the high velocities involved. These possibilities make the observation of 3I Atlas and its escort not just a snapshot of arrival, but a dynamic live event to monitor. The notion of companionship also plants intriguing philosophical questions. When we think of comets from other star systems, we imagine solitary wayfarers. But if they carry companions, then perhaps each interstellar visitor represents not just a chance lone sample, but part of a broader ejecta event in its home system. A breakaway of multiple bodies, a catastrophic ejection, or just a benign drift of paired fragments. In that sense, when 3I Atlas arrives, it might carry with it a small piece of its past environment in the form of its companion. That evokes the idea of cosmic siblings traveling in tandem across light years, preserved enough to still be together when they encounter our solar system. In more practical terms, astronomers will now adjust their monitoring strategy for 3I Atlas. Observatories will look not just at the main nucleus, but also attempt to track the companion's motion, brightness, coma development, and separation trends. They will examine whether the companion shows independent activity, whether its coma evolves differently, whether it displays tail structures distinct from the primary. In doing so, they may treat the system as a pair rather than a single object. That approach might yield insight into the origin event. For example, if the fragment split recently, we might see fresh dust emission. If the companion was long separated, its nucleus surface might be more pristine. The differences between the two may become laboratories for investigating interstellar origin processes. It is also worth reflecting on how this influences our understanding of frequency and detectability of interstellar objects. If interstellar visitors can arrive as pairs or small clusters, then we may be underestimating how many such bodies pass through the solar system because weaker companions may go undetected. That means our rate estimates for interstellar visitors may need revision, perhaps upward. It further suggests that observational surveys should seek trails of smaller objects along similar hyperbolic trajectories. In effect, the escort of 3I Atlas might be the first sign of a more complex population of comet-type objects from other systems. Moving beyond the technical, the presence of an escort evokes a sense of deep wonder. The idea that a body from another star system, millions of years old perhaps, is traveling with a companion, and that we can detect that companionship from our vantage point, invokes the notion of connection across the cosmos. It reminds us that the universe is not static but in motion. Objects exiled from one system may wander into another, and sometimes they may carry with them fragments of their origin. The notion of companionship among interstellar debris adds emotional depth to what might otherwise be seen as inert ice and rock drifting through space. For the first time, we might be witnessing not just a lone alien visitor, but a duo, a pair of cosmic travelers crossing the void together. Of course, caution is required. Astronomers will need to rule out alternative explanations, background stars, chance alignments, optical artifacts, but the Gemini images and the suggestion of an escort demand serious attention. If confirmed, the phenomenon is not a minor footnote, but a major shift in our conception of interstellar comets. It means that 3I Atlas is not just a single messenger, but potentially a small entourage, and that opens possibilities for richer data, deeper insight, and new theoretical pathways. In the broader scope of planetary science and astrophysics, the escort of 3Y Atlas also influences how we think about the evolution of small bodies in the galaxy. Most models of comet ejection from star systems consider single bodies being flung out by giant planets or stellar interactions. But if paired or grouped ejections are more common, then models must account for fragmentation prior to ejection, or for gravitational binding of small companions surviving long voyages in interstellar space. That in turn leads to questions about how many interstellar objects might reach our solar system with unseen companions, and what fraction of them might carry remnants of their original star system in the form of smaller bodies. Thus, 3I Atlas and its escort may serve as a key case study in interstellar small body dynamics. Another intriguing possibility: if the companion persists post-perihelion, as 3I Atlas moves away from the Sun and exits the solar system, we may get a chance to track both bodies as they recede. Monitoring how they diverge or remain in proximity could shed light on their binding, on the forces acting on them, and on how they survive or disintegrate post-solar passage. The companion might slow relative to the main body, or it may diverge more rapidly due to differential gas emission or solar radiation effects. In either scenario, the result will help build our understanding of how interstellar objects respond to the intense environment of the inner solar system, how they fracture, how they evolve, how they lose mass. It may also affect how we interpret observational signatures such as dust distribution, tail morphology, gas emission rates, and coma shape. For instance, if two bodies are shedding dust and gas, the resulting coma might be unusually broad, uneven, or shifting in unexpected ways. Some of the anomalies seen in 3I Atlas's tail development or coma elongation might now be reinterpreted through the lens of binary or multiple body behavior. In fact, the observations of unusual negative polarization in 3I Atlas's coma and its similarity to trans-Neptunian objects may take on new meaning if the system is composite. The escort adds a layer of complexity to what we thought was a relatively straightforward passive visitor. In summary, this unfolding scenario of an interstellar comet accompanied by a companion reshapes a number of key stories. The origin story of the object becomes more layered, not just ejection from a parent system, but ejection of multiple bodies, possibly fragmentation or binary survival. The passage through the solar system becomes more dynamic, not just one nucleus interacting with solar heat and the solar wind, but two bodies possibly interacting with each other and the environment. The observational story becomes richer, more data to glean, more complexity to unfold, more variables to track, and the philosophical story of connection of cosmic journeys and companionship across light years becomes more vivid. For scientists and astronomers, this means new targets, refining models of interstellar object ejection, tracking companions in hyperbolic trajectories, refining search algorithms for faint trailing bodies. For observational programs, it means allocating time to look not just for the bright primary body, but for nearby faint companions, noting relative motion, comparative activity, divergence, or convergence. For instrument designers and mission planners, it might raise the possibility of future missions targeting not just a single comet, but multi-body interstellar systems. And for the curious public, the notion of a dual-object interstellar visitor carries extra intrigue, a traveler and its sidekick in the cosmic dark. Simply put, the presence of a companion changes the narrative from one alien comet passes through to an interstellar pair crosses our sun's domain, broadening our horizon on what is possible. The journey of 3Y Atlas and its escort is a new chapter in the story of our solar system's encounters with the wider galaxy. It invites us to expand our imagination, to picture that other systems may send more complex emissaries than we had anticipated, that the loneliness we assumed of interstellar travelers may be less common than we thought, and that the boundary between our solar system and the interstellar medium may host more complexity than a single body passing by. The escorting presence near 3I Atlas continues to reshape not only how scientists analyze interstellar objects, but also how they imagine the very architecture of planetary systems elsewhere in the galaxy. If Gemini's revelation holds true, the existence of an accompanying body implies a far more intricate origin story, one in which objects are born, separated, and yet remain bound across unfathomable distances. The relationship between the two bodies could be gravitational, magnetic, or even a lingering vestige of a shared structural collapse. But whatever the mechanism, it implies a level of cohesion that survives the harsh vacuum of interstellar space. That endurance alone offers a hint about the physical robustness of matter formed beyond our sun's reach. One striking aspect of this event is the timing. 3I Atlas entered observational range during an era when instrumentation has reached levels of refinement capable of distinguishing the faintest glimmers of motion amid a comet's luminous coma. High-contrast imaging and adaptive optics now allow astronomers to separate companion light sources from the bright haze of outgassing material, something impossible in earlier decades. That means humanity is encountering its first interstellar visitors at precisely the moment when technology can record their subtleties. It's as if the cosmos waited until our eyes were sharp enough before sending emissaries complex enough to challenge our imagination. The idea of an escort traveling alongside 3I Atlas also broadens our perception of how materials from other systems might behave once they leave their birthplace. Interstellar space is far from empty. It teems with cosmic radiation, magnetic fields, and micrometeoroid impacts that can erode, reshape, or spin an object over millions of years. The fact that two bodies might remain coordinated after such a journey implies a stability far greater than expected. This could mean that the initial separation velocity was low enough to keep them coupled through mutual gravity, or that some form of cohesive structural bond, possibly frozen volatiles or magnetized dust, has preserved their pairing. Either way, the pair's persistence tells us that interstellar travel does not necessarily erase a system's internal relationships. The physical interplay between 3I Atlas and its escort is likely to generate complex dynamical behavior as they approach the Sun. The primary body, larger and more active, will experience stronger sublimation pressures, creating jets that alter its motion minutely but continually. The smaller companion might feel these effects differently, leading to oscillations in their separation distance. Such microdynamics could cause dust bridges or overlapping tails, features that might soon appear in deep field imagery. Observing these changes will provide a living laboratory for testing theories of binary comet evolution under solar influence, something never before possible with an object from outside the solar system. If the two bodies interact electrically as well as gravitationally, the consequences could be even more exotic. As charged particles from the solar wind strike the volatile-rich surfaces, they may produce differing plasma sheaths around each body. These sheaths could connect briefly through electric currents or shared magnetic fields, creating faint, transient auroras invisible to the naked eye but detectable in specific wavelengths. Such interactions could help explain irregular brightness fluctuations observed in the main body, suggesting a dance not only of dust and ice, but of energy fields linking the pair. Another captivating prospect lies in spectroscopy. If astronomers can isolate light from each object, they can compare their compositions directly. Should the escort's spectral lines show variations in volatile ratios or refractory dust, That would indicate differentiation before ejection. Perhaps the two bodies formed in different layers of their parent system's protoplanetary disk. That single comparison could tell us whether interstellar ejections select fragments randomly or tend to expel related materials. It could even reveal whether the system that birthed 3I Atlas once harbored planets, rings, or asteroid belts similar to our own. There's also a temporal dimension to consider. Interstellar comets like 3I Atlas may have spent millions or even billions of years wandering between stars before encountering ours. If the companion has truly been bound all that time, it must have survived countless gravitational encounters, bursts of cosmic radiation, and the slow decay of its surface ices. Studying its albedo, rotation, and density could show how interstellar exposure alters surface chemistry. In this sense, the companion is a time capsule, its material composition preserving a record of galactic travel, each layer of ice and dust a chronicle of cosmic weathering. From a theoretical standpoint, the pairing could support models that describe small body formation as inherently fractal. In those models, the collapse of dust in a protoplanetary disk often yields aggregates that form in clusters, not singles. During ejection, entire clusters could be flung outward, but only the most tightly bound pairs might survive the immense gravitational wrenching required to escape a star's influence. 3. I Atlas and its escort may represent the survivors of such an ancient fractal collapse, a duo that endured while the rest of their kin were torn apart. Their arrival in our solar system could therefore confirm that binary ejection is not an anomaly, but a natural outcome of planetary evolution. The escort's continued visibility also gives scientists a unique opportunity to study tidal evolution in real time. As the pair approaches perihelion, solar tides could stretch or torque their orbits relative to one another. If the companion begins to drift, astronomers could measure the rate of separation to estimate their mutual gravitational binding energy. That data would, in turn, yield clues about their masses and densities, key parameters for understanding how interstellar comets are built. This kind of information has never been gathered before for an interstellar object. It would refine every model of how such bodies form and survive. Beyond the technical implications, the discovery touches the philosophical heart of cosmic exploration. For centuries, humanity imagined comets as omens, singular wanderers crossing the sky. The idea that one could be accompanied, especially one from another star, introduces a narrative of companionship and endurance that transcends simple astronomy. It suggests that creation itself may prefer pairs, that the universe's fragments seek each other even as they drift through endless darkness. Such imagery captures the imagination in a way that pure data cannot. Two ancient travelers bound by invisible forces passing briefly through our sun's realm before vanishing again into the abyss. Astrobiologists also take note of what this companionship might mean for the transport of complex molecules. If both 3I Atlas and its escort contain organic compounds, their proximity could facilitate material exchange through dust transfer or gas interaction. That process might allow prebiotic molecules to remain shielded within interstellar bodies longer than if they traveled alone. It adds a new dimension to the panspermia hypothesis, suggesting that life-forming chemistry could hitchhike across the galaxy not on single comets, but on small consortia of objects that protect and enrich one another's chemistry during the voyage. From an observational perspective, the challenge now lies in persistence. The pair is faint, fast, and transient. Tracking them demands coordination across multiple observatories around the world, with data synthesis timed to fractions of a day. Gemini's initial images may soon be complemented by radar echoes or infrared spectra from other facilities, painting a multi-wavelength portrait of the first confirmed interstellar binary to grace our skies. Each observation will not only refine orbital parameters, but may reveal subtle gravitational influences between the bodies, perhaps even mutual eclipses detectable as minute dips in brightness. Even in a symbolic sense, the Gemini revelation reflects humanity's transition from passive observers to participants in a larger galactic dialogue. Every time an interstellar object enters our neighborhood, it carries information older than our sun, richer than any probe we have sent outward. That 3I Atlas might bring a companion transforms the encounter from a solitary visit into a cosmic conversation, an exchange between systems. Their presence challenges us to look beyond isolated phenomena and instead to perceive relationships, systems, and continuity across stellar boundaries. As the two bodies continue their journey through the inner solar system, astronomers will watch for subtle gravitational shears, dust-tail bifurcations, and shifts in activity rates. Each of these changes may reveal how interstellar pairs respond to intense solar input. If the escort eventually diverges from the main nucleus, that too will be valuable. It will mark the moment the gravitational bond finally breaks, demonstrating how far companionship can persist under the stress of stellar proximity. Whether they part ways or remain together, the data will become a benchmark for future observations of similar visitors. What is perhaps most profound about this event is that it expands our sense of cosmic possibility. Until now, humanity's experience with interstellar visitors has been limited to fleeting singular encounters. Gemini's detection of an escort transforms the paradigm, hinting that our galaxy may be threaded with pairs and groups of travelers silently crossing interstellar space. The next object we detect may not just be another lone wanderer, but part of a small convoy, evidence that the universe favors company even in the coldest voids. As 3I Atlas and its companion glide onward, they remind us that space is not empty but alive with stories still untold. Their passage is a fleeting intersection of two worlds, theirs and ours, yet it leaves behind a legacy of questions and wonder that will outlast their presence in our sky. Long after they have vanished beyond the reach of our telescopes, the image of a twin-traveled comet from another sun will endure as proof that even in the vastness between stars, bonds can survive, and that sometimes, even across light years, nothing truly travels alone. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us. What are your thoughts on Gemini confirming 3I Atlas isn't alone in space? We want to hear from you. Thank you for watching, and see you next time.